We have the problems in exercise 15.11. Let GCD M1 M2 equals to 1. Prove that A equivalence B modulo M1 and A equivalence B modulo M2 if and only if A equivalence B modulo M1 M2. Let's prove these problems. We have to prove from the left side to the right side. So, let GCD M1 M2 equals to 1. We have A equivalence, this is A equivalence B modulo M1. It means that A minus B equals to M1 times K for some K, and K in integers number. And then we also have A equivalence B modulo M2, this form. So we have A minus B equals to M2 times K, and K in integers number. We can denote A minus B equals to M1 times K. This is the first form, and the second form is A minus B. This is the second form, equals to M2 times K, the second form. From 1 and 2, then there exists X equals to B plus M2 times K equals to A plus M1 times K. Thus, A minus B equals to M2K minus M1K. We can factorize this form, so we get K times M2 minus M1. Notice that GCD M1 M2 equals to 1. We know that 1 can divide any number, so we get 1 divides M, 1 divides M1, 1 divides M2, and 1 divides M2 minus M1 times K, such that 1 divides M1 times M2. Thus, A minus B divides M1, M2, K, and for some K, and K in integers number. Or we can write this form to A equivalence B modulo M1 M2. So we can conclude that if A equivalence B modulo M1 and A equivalence B modulo M2, then there exists A equivalence B modulo M1 M2. And the second, we can prove from the right side to the left side. The first way, we let GCD M1 M2 equals to 1. We have A equivalence B modulo M1 M2. It means that A minus B equals to M1 M2 times K for some K and K in integers number. Remember that GCD M1 M2 equals to 1, and then we know that 1 can divide any number, so 1 can divide M1 divides M2 and 1 divides A minus B. And then, based on the definition, that say if there are two integers number S and T such that S M1 plus T M2 equals to D. Thus, B1 minus B2 equals to D times K. And we can substitute this form and we get S M1 plus T M2 times K. We can multiply by K. We get S M1 times K plus T M2 times K. We can move this is to left side and we get B1 minus SK times M1 equals to B2 plus T M2 times K. We may denote B1 equals to B2 equals to B. Then there exists a number A such that A equivalents B modulo M1 and A equivalents B modulo M2. So we can conclude that if A equivalents B modulo M1 M2, then there exists A equivalents B modulo M1 and A equivalents B modulo M2. So that's all for prove this problem. We have the exercise in 15.8. Show that if D divides M and D greater than 0, then A equivalents B modulo M implies A equivalents B modulo D. Let's prove this problem. So we know that D divides M implies A equivalents B modulo M, D greater than 0. D divides M, it means that M equals to D times K and K in integers number. And we have A equivalents B modulo M. It means that M divides A minus B, or we can write a minus b equals to m times l. L in integers number. We have two equations. The first is m equals to t times k. This is the first equation, and the second equation is a minus b equals to m times l. For this is the second equation. Then we can substitute the first to the second equation. So we get a minus b equals to m times l. We can substitute this form, a minus b equals to d times k times l. So we get d times k times l. This is the commutative law. For some k and l in integer number and t greater than 0, then we get d divides a minus b, or we can write a equivalence b modulo d. So that's all for proof these problems. And the next problem in exercise in 15.9, we have to prove theorem 15.4. Hint, the division algorithm may be useful. So let's prove this theorem. Theorem 15.4 say that if m greater than 0 and d equivalent r modulo m, where 0 less than or equal to r less than m, then a modulo m equals to r. This is the theorem, and let a equivalence r modulo m where 0 less than or equal to r less than m, then a modulo m equals to r. And then we can write a equivalence with r modulo m, or m divides a minus r, so a minus r equals to m times q for some q and q in integers number. We can move this side to the right side, so a equals to m times q plus r, and q in integer number, and 0 less than or equals to r less than m. So we can conclude that a modulo m equals to r. So that's all for proof these problems.